Good day, everyone, and once again we are back together. All right, so today we're looking at the IEB paper 2 for November 2023, and of course, if you haven't subscribed, please just make sure that you do the right thing, right? Otherwise, I know that your favorite uncle will always give you some good content. And let's dive right into this paper. Let's start with the multiple choice section, right? I'm going to start with question 1.1. So the question says to us, which one of the following name and formula combination is correct? Now I want you to note in this case, we've got first of all potassium dichromate. Now remember, the dichromate ion is Cr2O7, right? And this would be 2 minus, right? So definitely not that because it's missing a 2 there. And lead 4 oxide, that would be PbO2. That's what it would look like. Okay, aluminium sulfide. Okay, so remember sulfide in this case we would, okay, so aluminium is 3 plus, okay, but in this case when it comes to the sulfide ion, we would actually, in fact, yeah, that's definitely not how we would write it. And the last one, chromium 3 phosphate. Definitely the phosphate ion is 3 minus and chromium is 3 plus. So definitely it would look like that. So my correct answer would be D. Okay, right. Which one of the following pairs of compounds will have a higher boiling point than Y? Well, will X rather have a higher boiling point than Y? So we want X to have a higher boiling point. Okay, so first one, they say H2O versus hydrogen sulfide, right? And by the way, that's how you write a sulfide and not the previous one. Okay, so in this case, I would have definitely, I think A would be correct, right? Remember that water has got, strong hydrogen bonds, right? And in this case, hydrogen sulfide, definitely that would have dipole, right? So in this case, definitely water would have stronger intermolecular forces. Let's look at the next one, C2H6. Definitely the bigger the molecule, the stronger the intermolecular forces. We wanted this one, X, to have higher, so definitely not B. And if you look at C, you've got an alcohol there. This is a primary alcohol, okay? And in this case, we've got, a di-alcohol in that case. So definitely primary alcohols would have stronger intermolecular forces, okay? And finally, you've got fluorine versus chlorine. Definitely chlorine would have stronger intermolecular forces. Remember in the periodic table, the further down you go, the larger the molecule and so the greater the intermolecular forces. So definitely it would be, it would not be chlorine. It would not be fluorine in that case. So definitely the answer is A. All right, and let's go on to 1.3. Now they say, in which one of the following diagrams does the red dash line correctly show the formation of the hydrogen bond between two molecules? Now remember, the hydrogen bond is between the oxygen, right, in the hydroxide ion, or, in any, let me rather say, because we're dealing with hydroxide ions here, right? The oxygen in the hydroxide ion being attracted to the hydrogen in the adjacent hydroxide ion. Okay, so the only representation that looks correct is C, because it does actually do that. If you look at that, it's the hydrogen in the hydroxide ion with the oxygen in the hydroxide ion adjacent to it. Okay, so let's go to the next one. They say, which one of the following graphs shows the relationship between the activation energy for a reaction and temperature? Now remember, activation energy remains constant regardless of temperature, right? In this case, so in what we do know is that C would actually be the correct answer, right? Remember that activation energy is not affected by temperature. All right. Okay. Let's go on to the next one. The next question says a certain amount of ICl. Okay, so that's iodine chloride. Okay, is sealed in an empty flask and with a fixed temperature. They say the equation for the reaction that takes place is given there. They say which one of the following statements describes the changes that occur as the system proceeds towards equilibrium. So in this case, we have not reached equilibrium, right? We're still heading there. Right, so let's see the first statement. The rate of the reverse reaction is increasing. Absolutely, I agree. As we're nearing towards equilibrium, the rate of the reverse reaction definitely keep increasing. Okay, and then they say the concentration of ICl, I2, and Cl2 change at the same rate. Absolutely not, right? Remember, in this case, we have not reached equilibrium. Okay, so statement 2 would be incorrect. Now, statement 3 says the concentration of Cl2 increases. Now, please remember, the rate of the forward reaction as we get towards equilibrium is still higher than the rate of the reverse reaction. So statement 3 would actually be correct. And so the correct answer there is C, which is 1 and 3 only. Right, going on to the next question. They say so this is the ionization constant of a base. The Kb values of two hypothetical bases are tabulated. Okay, now look at that. At 25 degrees, you can see that this guy has got an ionization constant of 4.4, okay, and the other one 5.6. So YOH has got a higher ionization constant, right? So in this case, that means that this is a stronger base, okay? Now they say to us, aqueous solutions of bases and their chloride salts are compared. All four solutions have the same concentration. Which base solution will have a higher pH and which chloride solution will have a higher pH? All right, now if I look at that, definitely this guy, Y, okay, will have a higher pH. So the answer is between C and D, right? But now as a chloride, so what happens in that case? It means that Y would be able to also dissociate very easily as well, right? So I would actually choose D as my answer. Okay, right, so they say an impure copper electrode with which contains small amounts of gold and zinc is purified by electrolysis, right? During the process, a sludge forms beneath the anode. Now remember, sludge is formed because in that case it means one of the elements, okay, would not be able to be oxidized in that case, right? It wouldn't actually participate in the reaction. So they say, why is gold the only metal found in the sludge? So it means that gold is the one that did not participate in the reaction. Okay, so let's look at the first one. They say copper and zinc are oxidized, but gold is not. Absolutely true, right? That is definitely true. They say gold ions are moved easily, are more easily reduced than copper. That is not true. Okay, in that case, remember that gold did not even participate in the reaction. Gold reacts with the electrolyte. Nope, that's not even true. The amount of gold in the electrode is too slow. That's not true either. Right, next one. They say cations can pass through a component X while anions cannot. Okay, This looks like something that is familiar. They say, which one of the following might component X be or represent? Okay, the first one, the diaphragm. No, not the diaphragm, but it's actually the membrane of an electrolytic cell, right? If you look at my video on the chloroalkali industry, right, you'd see that this would definitely be the correct answer. Okay, so the last one, the almost last one, okay, they say the alcohols of a homologous series form a homologous series. Which statement is correct? Alcohols have similar physical properties. That's not true. Some can be gaseous and some can be liquid, right? Or rather, actually I should say liquid, right? The next one, they say similar chemical properties. That is absolutely true. This is what makes a homologous series, right? Because they've got the same functional group, and through that functional group, they share similar chemical properties. Let's look at C and D. It says the same molecular formula. Remember, that's not true, because if you take ethanol versus methanol, they wouldn't have the same molecular formula as well as a structural formula. So D is also out of the question, right? Now, the last question, they say when red bromine water is added to a hydrocarbon. So remember that it means that this hydrocarbon has to be an alkene, right? They say the color disappears immediately. In fact, this is what confirms that it's an alkene, right? So they say from this, it can be concluded that the general formula of the hydrocarbon, nope, that cannot be A, that's not an alkane. They say the hydrocarbon undergoes a hydration reaction with bromine. That is not true. Okay, they say the red-brown color fades immediately in the presence of any hydrocarbon. That is not true. That leaves D as our only option. The hydrocarbon undergoes an addition reaction with bromine, and remember that if we've got alkenes, they would actually undergo an addition reaction with a halogen. Okay, so D is definitely the correct answer. Well, ladies and gents, that makes the multiple choice section. Let's go on to the next question. Right, so on question 2, they say the structure of a solid sodium thiosulfate is shown in the diagram. Okay, so there you've got sodium ions over there and the sulfate ions. Right, now the first thing that we are being asked is define electronegativity, and I hope that most of us have got this theory, right? So remember what electronegativity is. It's the measure of the tendency of an atom to attract electrons towards itself, right? Or a bonding pair of electrons, right? So in this case, I won't write that out. Okay, so remember, it's the tendency to attract, okay, electrons. It's the measure, rather, of the tendency to attract electrons, right? So please remember that definition. Okay, that's something that you just need to keep in mind. Right, now in the next question, they say describe a covalent bond. Right, remember, by definition, again, a covalent bond is defined by an equal sharing of electrons, right? Okay, so when we've got a sharing of at least one pair of electrons, right, by two non-metal atoms. Okay, right. Sometimes you can even just define it as a bond occurring between atoms within molecules. Okay, so when there is a bond between atoms in a molecule, so if you look at that, that's a covalent bond that is formed. All right, because we've got equal sharing of electrons. Right, the next question, they say which two atoms in this compound are held by polar covalent bonds? Explain. Now remember, in this case, you've got sodium thiosulfate, right? But the ones that are held by polar covalent bonds would be sulfur and oxygen. Okay, so that would be sulfur as well as oxygen. Okay, so that's S and O. All right, and they said, remember, they said you must explain. Okay, so remember that when we talk about polar covalent, it means that there's an unequal sharing of electrons, right? The electronegativity of sulfur is not equal to that of oxygen, so there's definitely an unequal sharing of electrons. Okay, so you can say unequal sharing of electrons, or you can even state the fact that they've got different electronegativities. Okay, right, the next question. They say to us, an aqueous solution of sodium thiosulfate is prepared. What is meant by the term solution, right? So remember, when we are forming a solution, right, first of all, it's a mixture, or rather, yeah, it's a homogeneous mixture. Homogeneous mixture of solute, and in this case, when we've got a solute and a solvent, right? Remember, that's what would constitute a solution, right? Of solute and solvent. Okay, right. So they said identify the solvent in the solution. Of course, what would you do? You'd put this in water, isn't it? So you can say H2O, or you can just simply write there water. Okay, right. So the next question, they say to us, name the bonds or forces in sodium thiosulfate that are broken or overcome when the compound dissolves. Now, please remember, right, these would be ionic bonds, right? That's why it's able to ionize like that, okay, to form the sodium ion as well as the sulfite, and the sulfate ion. So in that case, it would be ionic bonds, right, that would need to be broken. All right, so the next question, they say define electrolyte. Okay, so an electrolyte in this case is a substance that can conduct electricity, right? Yeah, by forming free ions, or you can say that it's a dissolved solution that is able to conduct electricity by forming free ions. Right, you can write that down for yourself. Okay, I will not do that. Okay, and finally they say, is this solution an electrolyte? And the answer is simple yes. Okay, right, you can see that it ionizes, and therefore it would be in a position to conduct electricity. Okay, right, and that would be 14 marks, ladies and gents, and that's the end of question 2. I hope that you've got this. I mean, it was mostly theory, so you should be having that on lock. All right, let's move on to the next question. And now we jump into question 3. All right, so they say to us, we've got sodium, solutions of sodium disulfate and hydrochloric acid react as follows. Right, you've got a reaction there. They say define reaction rate. Remember that reaction rate is the change in the concentration of products formed or reactants used per unit of time. Right, I'm not going to write that down. Let's go on to the next question. They say the effect of concentration of sodium disulfate on the rate of reaction was investigated. In each experiment, 5 cubic centimeters of 0.1 moles per cubic decimeter of hydrochloric acid was added, right? So they want to know, okay, it was added to 25 cubic centimeters of sodium disulfate solution, right? And I want us to quickly observe the trend here, that for every single time that they changed or they increased the concentration of sodium disulfate, what happened is that the rate increased. Remember, rate, it's per unit of time, right? So you can see that there's an increased rate of reaction there. Right, now let's see the questions. They say, consider experiment 5. So we're going to focus on this guy here, right? They say in which the concentration of sodium thiosulfate was 0.1. Prove that hydrochloric acid is the limiting reagent. Do not round your answers. Okay, so let's do this. We have to find out what is the number of moles of hydrochloric acid as well as sodium thiosulfate. So first of all, I'm going to say, right, let's find out the number of moles of sodium thiosulfate, okay? And in this case, remember I'm given the concentration as well as the volume. So what I'm simply going to do, there's the volume of sodium thiosulfate, and there is the concentration on experiment 5. So that's going to be concentration times volume. So this gives me 0.1 multiplied by, now remember 25 cubic centimeters, we have to convert it to cubic decimeters. We divide it by 1,000. Okay, so that will give me 0.025. Okay, right, so when I multiply that, I get 0.0025 moles of sodium thiosulfate. Now the question is, so for these amount of moles of sodium thiosulfate, how much hydrochloric acid would I need? Okay, so I'm asking the question based on that reaction. So the reaction says for every 1, you need 2 times the amount of hydrochloric acid, right? So I'm going to look at that based on the reaction. So therefore, how many moles of hydrochloric acid would I need? I'd need twice as much, right? So that means for this amount of sodium thiosulfate, therefore I will need, okay, so number of moles of hydrochloric acid, this is what is needed, okay? In this case, it will be twice as much, which is 0.005 moles, right? However, now I'm going to compare it with the amount of moles that I actually have, right? So now let's calculate the number of moles of hydrochloric acid. Okay, so number of moles of hydrochloric acid, we said we've got 5 cubic centimeters and the concentration is 0.15. So this is going to be 0.15 moles multiplied by, that's the concentration rather, multiplied by the volume, which is 0.0005. Okay, so I just took 5, divided it by 1,000, right? So that's 5 divided by 1,000. Okay, actually I added an extra 0 there. So this is 0.005. Okay, so now what I'm going to do is calculate there. So we're going to say 0.05 multiplied by 0.15. And you can see that gives us a very tiny number, 0.0075 moles. Right, now we need to make a conclusion, right? So in this case, the amount of hydrochloric acid that we would require if sodium thiosulfate were to be a limiting reagent is 0.05, right? But can you see that the amount that we actually have of hydrochloric acid is much, much tinier than what we need, right? So therefore it means that hydrochloric acid will therefore be the limiting reagent. So HCl is the limiting reagent. Okay, I hope that makes sense. Alternatively, what you could have done is calculate the number of moles of hydrochloric acid, right? And ask the question how much of sodium thiosulfate you need, and you'll see that the amount that you need is more than the amount that you have of sodium thiosulfate. So therefore it means sodium thiosulfate would not be the limiting reagent, thus making hydrochloric acid the limiting reagent. Okay, right, so this would be the limiting reagent. Okay, right, I hope that makes sense, ladies and gents. Right, now remember, every time you've identified the limiting reagent, so it means this is going to be the driver of the reaction. Remember, it means that this is the one that's going to limit to what extent you form products. It's going to determine to what extent you actually use the other reactant as well. Okay, right, now let's go to the next question. They say to you, calculate the number of sulfur atoms in the precipitate produced when the reaction goes to completion. Right, now remember, you use the limiting reagent. So we know this is the amount of hydrochloric acid that we have, right? So the reaction says for every 2 moles rather, of hydrochloric acid, I will produce 1 mole of sulfur, right? So what you simply do is for every 2 moles of hydrochloric acid, you will produce 1 mole of sulfur, right? So the question is for 0.00075, okay, what will be the amount of sulfur moles that will be produced? Okay, so if you cross multiply there, you'll have 2n is equal to 0.00075, and if you divide by 2, that will give you the amount of the number of moles rather. Okay, now of course you could have just seen this by simply saying that the amount of moles of sulfur were half the amount of hydrochloric acid, right? So 0.00075, and I'll divide that by 2, I get 0.000375. Okay, they said not to round off. Now remember, ladies and gents, what did they ask me? The number of atoms, right? So I am going to use Avogadro's constant and say, look, to get number of atoms, remember, Avogadro's number, so this is n divided by Na, right? Where Na is Avogadro's constant, right? So we're looking for number of atoms, which is this guy here. We've got number of moles, which we just obtained from there. And now we're going to look for, can I just make some space here? Right? So which means number of atoms would be number of moles multiplied by Avogadro's number. So that's 0.000375 multiplied by Avogadro's number. And please remember, in this case, that's 6.02 times 10 to the exponent 23, right? So now what we're simply going to do there, just multiply that number, okay, multiplied by 6.02, okay, exponent 23, okay, we get that huge number there, which is 2.26 exponent 20 atoms. Okay, right, I hope that makes sense, ladies and gents. Right, let's go on to the next question. So they say to us, plot a graph of reaction versus concentration rate of reaction rather, reaction rate versus concentration. Draw a line of best fit. An extra copy of the graph is provided. Okay, all right. Now, fortunately, they've already indicated the values for concentration there. They've got a scale. Now, let's look at the scale that we can take for rate, right? So if you look at those values there, I would say what would be a suitable scale that we can actually assume there? I would say, okay, so I just want to take those values there and just make sure that we have them. So a scale, in this case, we're starting from 0.05 to 0.005 to 0.05. So I think a good scale, if we said that would be 0.01 there, okay, 0.02. Okay, remember the scale that you choose must actually be more than half of your axes, right? So 0.04 and 0.05. Okay, right, now the values that you have, so what I've done is just to take a picture of them so that I make sure that we have them. So we've got for concentration 0.01, which is here, okay, and 0.005. Now if you think about it, this would be 0.001. Okay, so the increase in terms of the step size is 0.001, right? So 0.005 would be here, okay, and then the next value 0.02 and 0.009. Okay, so 0.02 and 0.009, this is exactly there. Okay, and the next one 0.04 and 0.22, there it is over there. Okay, and 0.08 and 0.042. Okay, right there, as well as 0.1, okay, 0 and 0. Okay, so that's that value there. All right, so what we're going to have to do is try to perhaps just take a line of best fit if it let's see, okay, yeah, I'm going to take that as my line of best fit. Okay, it would make sense for it to start at the origin. Okay, and of course there I can see several of my values would actually be included in that graph. Okay, there we go. That is what our graph would look like, and I hope that you're getting the gist of how to draw those graphs. Okay, right, now they say to us determine how long, okay, and they say determine how long in seconds it would take for sodium thiosulfate solution of concentration 0.03 moles per cubic decimeters to react in this experiment, right? Now remember that rate is per second. So what we're going to do is we're going to have to read off from this graph. Okay, so I'm going to take my ruler and say, right, let's look for 0.03 concentration. Okay, so it is, no, actually, I'm taking the incorrect one. 0.03 would be there. Okay, and remember, you use your line of best fit to obtain that value. So I would say, well, from what we read off from the value, it looks like it's going to be 0.015. Okay, so that's on rate, but we're looking for time. So time, okay, let me continue on my blue color. So time in this case would be 1 divided by the rate. Okay, and so that's 0.015. Okay, right, so I read that that's called interpolation, right? From the graph, we read it off from the graph so that we get that value there. So we said this is going to be 1 divided by 0.015. Okay, right, so it looks like it's going to take 66.67 seconds, okay, or let's say 66.7 seconds. That is the amount of time that will take. Okay, so remember we got the value from here, and this would be 0.015. Okay, right, so they say state in words the relationship between concentration of sodium thiosulfate and the rate of the reaction. And I mean, we can see that there. It's a linear relationship. As concentration increases, right, the rate of the reaction also increases. You can also say there that the rate of reaction is directly proportional. Okay, rate of reaction is directly proportional, right? Now, the reason why I can use directly proportional in this case, I can see firstly that's a linear relationship, is directly proportional rather to the amount or to the concentration of sodium thiosulfate. Okay, sodium thiosulfate. All right. Or you can say as the concentration of sodium thiosulfate increases, so does the rate of reaction. Okay, right, now the next question says, when the temperature, when the effect of temperature on the rate of the same reaction was investigated, the graph below was obtained, right? Now you can see there's an increase there. As I increase temperature, so does the rate of reaction. Of course, it doesn't increase in a linear way this time. It seems it's an exponential increase, right? Now they say use the values from the graph to determine the temperature rise required to double the rate for this reaction. Okay, once again, this is going to be a, we're going to have to read off from the graph, right? Let's take any time when the rate doubles, right? Let's say when we start from 0.02 and double that would be 0.04 and get the corresponding time value for that. Okay, so let's find the temperature at, okay, so the temperature at 0.02. So that looks like 36, 7, 8, 38. That's 38 degrees. Now, double that rate would be at this point here, 0.04. That's twice 0.02. And I see there the corresponding temperature value would be 57, is it? I mean 52 rather. Okay, so that's 52. So let's find out what is the temperature difference between those two values, right? We're simply going to say 52 minus 38. That's 14 degrees. So the temperature, the change in temperature that's required would be 14 degrees Celsius. Okay, right, so I showed you how to do that by reading off from the graph. You could have taken any other rate where it actually doubles. You could have read off from 0.03 to 0.06. Nothing wrong with that. I'm sure you would arrive at the same conclusion. Right, now they say to us, explain the effect of increasing temperature on the rate of reaction in terms of the collision theory. Now remember, we say that an increase in temperature, right? An increase in temperature, will increase the average kinetic energy. The average kinetic energy of the molecules, isn't it? Kinetic energy of molecules. Okay, and now it means that there'll be more collisions that take place. Okay, so that will increase more collisions per second. Okay, and more specifically, now there are more molecules with sufficient kinetic energy, right? So there'll be more molecules with sufficient kinetic energy. And note that when we say sufficient kinetic energy, it's kinetic energy that is greater than the average, the activation energy, right? And in this case, it means that this will increase the number of effective collisions per second. Okay, increase in effective collisions per second. Okay, collisions. Remember, effective collisions are ones that have sufficient kinetic energy in them and correct orientation, right? So increase in the number of effective collisions per second. And that is why the rate of reaction will increase. Okay, right. I hope that makes sense, ladies and gents. Okay, so that is it when it comes to this section. I hope that you enjoyed it. Let's go on to question 4. Jumping into question 4, they say consider the equation below, which represents a hypothetical equilibrium reaction rather. Okay, so there we've got the reaction. We've got, so they're asking us, why is the temperature at 40 degrees specified? So they've given us a Kc value there, and it's important for them to give us a temperature, a specific temperature. Remember that Kc value, or rather the equilibrium constant, is dependent on temperature. Okay, so Kc is dependent, or you can say changes with a change in temperature. Okay, on temperature. Okay, actually that should be dependent on temperature. Right, now they say to write down the expression for the equilibrium constant, right, for this reaction. Now remember that when we have the Kc expression, it's always molar concentration of our products. Okay, so that's going to be A3B2, right, divided by the molar concentration of our reactants, right? So this is going to be, now please, I want you to note in this case, A is a solid, so we do not include it in the expression, right? But B is certainly to be excluded, so that would be B squared. Remember that the coefficient becomes the power in that regard. All right, so that's what we'd have. Right, now they say to us 0.3 moles of B was added to 2 cubic decimeters. Okay, that's very important. Okay, a reaction vessel containing some of A. The container was sealed and allowed to reach equilibrium at 40 degrees, right? At equilibrium, there were X moles of A3B2, right? Use the expression to set up a mathematical equation that can be used to solve for X, right? Now remember, we're going to use our table here, right? So I'm going to just quickly set up that table. Okay, so we would have initial, okay, that's in moles, and please remember to put the SI units, right? And that would be change, also in moles. Not sure why I made such a small space. That's equilibrium, that's also in moles. And please don't forget the equilibrium concentration, right? And that would be in moles per cubic decimeters. Okay, because of space there. Right, so now in this case, I've got, firstly, my reactants, which are 3A, that's 2B, and in this case, my product, which is A3B2, which is a gas. Now, even if A is a solid, we do include it in the table. However, we do not include it in the equilibrium expression. Of course, some of you like also having just a separate row for ratios. Nothing wrong with that. I've just written my ratios right there at the top. Okay, so initially we started with 0.3 moles of B, right? And in this case, they say 0.3 moles of B were added to the reaction vessel with some of A, right? So we don't know how much of A. The container was sealed and allowed to reach equilibrium, right? Now note, they did not say anything about the product, so assumption is that we started with nothing, right? They say at equilibrium, there were X moles of A3B2, right? So there were X moles of this guy, okay, at equilibrium. Now, I want you to note, if I started with nothing and at the end I end up with X, how much did I produce? I must have produced an X amount, right? So, and then again, so what would I do? So in this case, I'm going to use my ratio. For every one, there's two of those. So for every X, there'll be 2X. Okay, so for every one, there'll be 3 of that. So this will be 3X. Okay, so I'm not too worried about A because remember, that's a solid. So at the end of the day, we don't quantify it in terms of concentration, right? So I started with 0.3. I used 2X. How much do I have at the end? I would have 0.3 minus 2X. Remember, that's our reactant, right? And then equilibrium. Remember now, what do I have? That would be 0.3 minus 2X, right? Divided by, that's the concentration. So it's number of moles divided by the volume. So that would be divided by 2. And here you would have X over 2. That's the amount of A3B2, right? All right, so this one cannot be quantified in terms of concentration, okay? Right, now they say to us, use the Kc expression you've set up to write down an equation, right? That can be solved. All right, so now remember the Kc expression. We had the molar concentration of A3B2, right? So that would be X over 2. Okay, so I'm just going to substitute because we had already written the expression down, divided by, in this case, I've got 0.3 minus 2X divided by 2. Okay, now if you wanted to simplify your equation, both of them are divided by 2, so you can simply just multiply by 2. What you do at the bottom, you do at the top. Okay, that cancels out that 2 there, cancels out that 2, so you end up with X divided by 0.3 minus 2X. Okay, so that actually makes it much easier for you to solve. Okay, right, now they say to you, the equation for the equilibrium reaction is written here, okay? Simplifying and solving the mathematical equation obtained in 4.3.1, gives two answers, right? They say then the number of moles of A3B2 at equilibrium. So you get two answers, either 0.56 or 0.04. Let me just check. Were we given the Kc value? Oh yes, we had been given the Kc value. So we would have substituted that value there, which is 1.65. Okay, so if you wanted to actually simplify even further, that would give you x equals to 1.65 into 0.3 minus 2x. Okay, and of course, you can simplify this as much as possible. Okay, right, so they said it does give us this answer. And they say to us, explain why x is equals to 0.56 is impossible, right? If the container originally contained 0.3 moles of B. Now remember, what was x? Okay, so x would be the number of moles at equilibrium, right, of A2B3, right? Now, if we get 0.56, okay, now I want you to please note, in this case, if x is 0.56, in fact, if we go to this amount here, now look at the amount of B, it means that you'd have 0.3 minus 2 times 0.56, which gives you a negative value. So what is it trying to tell you? It's actually telling you that you've got more B at equilibrium than you did when you started. So in that case, that would be impossible, right? So they say explain why it is impossible. Okay, so because there would be more moles of B at equilibrium than we started with. In fact, actually, maybe that would not be an correct explanation. Rather, let's say it would result in negative moles. It will result in negative moles of B at equilibrium, right? At equilibrium. Alternatively, what you can say is that it would mean that you used more moles of B than you actually had, right? That negative answer is actually telling you that you used more than 0.3 moles, and that's not possible, right? You can't use more than what you have, right? Okay, you can also express it in that manner. Right, now they say to you, calculate the equilibrium concentration of B in the reaction vessel. Okay, so please remember, the correct answer would have been 0.04, right? So the number of moles of B, right, at equilibrium is 0.3 minus 2x. So the equilibrium concentration, remember, in this case, would be 0.3 minus 2 times, now x is 0.04, okay, and this is divided by 2, which is the volume. Okay, so I'm not bothering much with writing down the the full expression, because we had already done that. So that's 0.3 minus 2 times 0.04, right? This is divided by 2. Okay, so we get an answer of 0.11 moles per cubic decimeters. Okay, right, I hope that you got that, ladies and gents. Right, now let's go on to the application now of Le Chatelier's principle. They say the reaction is repeated with a catalyst with all other conditions remaining the same, right? Circle the correct option between the brackets. Okay, so they say the value of Kc, remember, Kc can only be affected by temperature, so Kc will remain the same. Okay, and they say the value of delta H, okay, remember, even if you use, at a different temperature, right, the enthalpy change remains the same. Right, now they say to us the graph of the original reaction rate versus time is given below. On the same set of axes, draw the graph to show the effect of a catalyst for time, right? From time t is equal to 0, right? So what would the effect of a catalyst be? It would just be an increase in the rate of the reaction, right? So you would have a graph that looks like that, okay? And of course the other graph would be also a little bit more steeper. All right. Okay, sorry for my wiggly hand. You guys are making me nervous. All right, so there we go. So that would be the graph with a higher reaction rate, okay, because of the effect of a catalyst. Now let's go on to the next question. They say to us we've got the reaction written below is carried out at a lower temperature. Now remember that we had delta H less than 0. Now the moment that we've got delta H less than 0, it tells us, I always say look at Pac-Man, okay? So our Pac-Man is facing to the right. It means that heat is to the right-hand side. So that is actually an exothermic reaction. The forward reaction is exothermic, right? Now, if you're going to lower the temperature, you always favor the exothermic reaction. Okay, so in that case, it means that the forward reaction will be favored. So it means the yield should improve, right? They say circle the correct option. Okay, between the brackets where appropriate, they say the yield, okay, definitely we will say increases, right? And they say explain the answer in 4.5.1 by applying Le Chatelier's principle, right? Now, we will say an increase in temperature, all right? An increase in temperature favors the reaction, the exothermic reaction. Okay. Right, so remember, we are taking away temperature, and Le Chatelier's principle is saying, let's replace the temperature. And where's temperature? On the right-hand side, right? So if we take away, of course, the reaction moves in such a way that to try and replace what we've taken away, right? So a decrease in temperature, a decrease, that should have been a decrease in temperature, okay, favors the exothermic reaction, right? The forward reaction is exothermic, okay? The forward reaction is exothermic, okay? Therefore, forward reaction is favored, right? Reaction is favored. Therefore, the yield will increase. Increasing the yield. Now, ladies and gents, another way that you could have expressed this, right? You can simply say that the lowering of temperature, okay, will favor the reaction that will replace, or that will that will, let's say that will replace the amount of temperature that has been taken away in accordance to Le Chatelier's principle, right? The forward reaction is favored, okay, and therefore the yield increases, okay, right. And finally, they're asking about the value of Kc. So remember, if my products increase, right, because of temperature, then it means that my Kc will increase as well. Okay, so that is how the cookie crumbles for this question 4, right? And we will move on to the next one. I hope it's been helpful, ladies and gents. So we start with question 5. All right, let's go right on ahead. They say the acid, so we've got a solution of a hypothetical weak acid. So that is very important to note there that our acid is weak. And they say, and sodium hydroxide react. Remember that sodium hydroxide is a strong base, right? So in this case there, we're given the reaction between the two. They say classify the acid in terms of the specific number of protons donated. I want you to note in this case, this acid has actually 3 protons in it. So therefore it is, they say the acid is, it's going to be triprotic. Okay, so it's going to be a triprotic acid. Okay, they say consider the ionization reaction of a weak acid H3A represented by the equation below. Right, so there's that equation that they've given us. They've given us the Ka values, right? Now, I want you to keep in mind, Ka is the ionization constant for the acid. So that means that if I look at this guy, it's definitely going to be this one associated with a weak acid, right? So they say to us, the 2 Ka values circle the value that is most likely to be the one. Okay, so for the weak acid, it's definitely going to be this guy. All right, so they say H2A minus is amphoteric. Okay, so it means it can behave as both an acid and a base. They say circle the correct option between the brackets. In the ionization reaction shown above, H2A is acting as, now I want you please to note, in this case when we take the reverse reaction, H2A minus, right, starts as H2A minus, but it becomes H3A. So that means this guy must have been the base because it received a proton, right, and therefore became H3A, H3A, right? So in this case, it means that it acts as a base. Okay, right. The next question, they say, write an equation for the hydrolysis reaction of H2A minus when it acts as an acid. Now, what are we going to do? We're going to take that reaction, right, H2A minus, okay, and we are now going to react it with water, H2O, okay, and we wanted this guy to behave as a base, right? So what are we going to have? We're going to have, in this case, it's going to give us it's going to give away rather, right, when it acts as an acid actually. So yeah, it's going to be HA, that's 2 minus. Remember, it has lost 2 protons now, right, plus H3O plus. Okay, right, so that's how it's going to go. It's going to give away that hydroxide ion and in this case become H3O plus. Okay, right, now the next one, they say dissociation. The salt Na3A dissociates completely in water. Okay, so we want to define dissociation, right? Remember what dissociation is? It's just the splitting of an ionic compound into its ions, right? So it's when an ionic compound dissociates, or rather splits into ions. Okay, right, I'm not going to write that down. Okay, so the next question, they say complete the balance and balance the equation for the dissociation of Na3 A. All right, so remember it gets into water. So we've got 3 of those, and remember sodium has got in this case 1 plus, so it has to be 3 of them, and it means that A, right, you needed 3 Na pluses, so this would become A3 minus. Okay, so that is what it would look like. They say circle the correct answer between the brackets. Okay, Na3A is, okay, so note, remember that this guy comes from sodium, right, which would be a strong base, right? So a strong base would give a weak ion, right? So so in this case, it means that it would give a weak ion. And then so that means that you have taken a strong base and a weak acid to form this guy, right? So it definitely should be basic. Okay, right. So the next question, they say a grade 12 learner, the grade 12 learners were required to standardize a sodium hydroxide solution by titration, right? They say Zandi prepared a standard solution of H3A with a concentration of that in a volumetric 200 cubic centimeter volumetric flask, using after rather filling the flask to the mark on the neck, she put the stopper on and mixed the solution well to ensure it is homogeneous. Right, now they want us to calculate the mass of H3A. Right, now first of all, we've got the concentration, we've got the volume, right, of that solution, right? So in this case, we've got number of moles, or rather let's use concentration, is mass divided by molar mass times volume. Okay, so our concentration is 3.81 times 10 minus 2. Okay, we want the mass. The molar mass is given as 192. Okay, and the volume is 200 cubic centimeters. Please remember, we need to convert that to to cubic decimeters, and we do so by dividing by 1,000, right? Okay, so in this case, if I cross multiply, let's make that over 1. Okay, so we're going to use a calculator. Okay, so 3.81 exponent negative 2 multiplied by 192 times 0 0.2. I get 1.46. So my mass will be equal to 1.46 grams. All right, hope that makes sense. Right, now they say to us, why is it important that the standard solution be homogeneous when doing titration? Very important. We need a specific concentration in this case so that our results are accurate, isn't it? Okay, so the concentration, okay, let's say the concentration must be accurate, must be specific, okay, so that our results are accurate. Okay, right, so that is the reason we must actually standardize that solution. Now, in this case, they say Zandi pipetted 25 cubic centimeters of sodium hydroxide into a conical flask. She added a few drops of indicator solution and titrated with a standard H3A solution. She repeated this procedure several times and obtained an average titration volume of 32.6. Okay. Now, they say to us, consider the available indicators, right, shown below. Okay. They say which one of the indicators would be suitable for this titration. Now, remember, okay, so in this case, you had sodium hydroxide, which is a strong acid, right, inside, your volumetric flask with the indicator. So in this case, it means that we need something that's going to be in the base range, right? But in this case, because we are titrating with a weak acid, we end up with an acidic, or rather a basic solution, right? So if I look at that, what's measuring across the the basic range, would be definitely phenolphthalein. Okay, right. So I would say definitely that's phenolphthalein there. Okay. And then they say state the color range that would be observed at the endpoint in this particular titration. Think about it. We're moving from a deeply basic solution and we want to titrate it. So it would move from pink to colorless, isn't it? So it would be pink to colorless. Okay, right. Now the next question, they say calculate the concentration of sodium hydroxide solution that Zandi would obtain. Okay, write your answer to 3 decimal places. Right, so first of all, we've got 25 cubic centimeters of the sodium hydroxide, right? And remember, we already had the concentration of, we had the concentration there, 3.81, okay? Right, so, and we've got, by the way, let me check, we've got the concentration, or rather the volume of H3A, right? So I'm going to use my titration reaction. So that's CAVA over CBVB, K is equals to NA over NB. Now, if you haven't seen me do these reactions before, please just watch my, so I'm going to name this A and this would be my B. Okay, so concentration of the acid, okay, we had that 3.81 there. Okay, so that's going to be, it's 3.81 times 10 minus 2, okay? And the volume of the acid, remember, they said to us it's 32.6, I believe, okay? All right, and then I'm looking for, in fact, I'm looking for the concentration of the acid, sorry. And it doesn't matter which one you call A, which one you call B, but in this case, actually, I just swapped them around, I realize. Okay, so I actually should have said, this is going to be my A. Yeah, actually, I was correct. The 3.81, that's for, no, yeah, definitely. Okay, so I was actually quite correct. Okay, so that's 3.81. Sorry for erasing that. Okay, so that's 3.81 times 10 minus 2. The volume of the acid, in this case, we said that's 32.6. Okay, concentration of the base. Okay, that's what we want. And they said the volume was 25. And now, please, I want you to note, ladies and gents, the ratio here is 1:3. So this is going to be 1/3 over there, right? And all we do are some gymnastics, right? So the concentration of our base, in this case, let's calculate there quickly. So I am simply going to multiply those. So that's 3.81 exponent negative 2 multiplied by 32.6 multiplied by 3, right? So we get that answer there. And I'm going to divide all of that by 25. Okay, and I get a concentration. And remember, they said to 3 decimal places. That's 0.149. That's moles per cubic decimeters, right? So that is the concentration of sodium hydroxide, which is our base. All right, now they say Mike also used 200 cubic centimeters flask to make his H3A standard solution. He recorded the mass of H3A crystals that he transferred into the flask. He dissolved the crystals in distilled water, then added more distilled water. You see, to the above. On the neck of the flask, he carefully removed some of the solution with a dropper until the bottom of the meniscus was on the mark on the neck of the volumetric flask, right? They said then he placed the stopper on the flask and mixed the solution well, right? He calculated the concentration using the recorded mass of the volume of 200 cubic centimeters, right? Right. So in this case, they say consider Mike's method of preparing his standard solution. Circle the correct option rather between the brackets and explain the answer. Okay, so when we look at what Mike did, they say the actual concentration in Mike's H3A solution will definitely be less than, right? Because remember, what did Mike do? He added more water in that case, right? So in this case, there was a point where I highlighted that he added more distilled water. So in that case, that's the reason why it will be less than. Okay, right. So more water was added. Okay, right. All right, and the last one, they say consider Mike's calculated sodium hydroxide concentration after this titration and circle the correct option between the brackets. Mike's calculated sodium hydroxide concentration definitely would be higher, right? So if I use the concentration of the other solution, if it was lower, right, then it means that my answer for the other one would definitely be higher than. Okay, right, and they say to us, briefly explain. Okay, right, so remember what would happen this time. It means he would need more H3A, right, to try and neutralize the same amount of sodium hydroxide, right? So yeah, that's essentially what would happen. So more H3A, okay, would be required. Okay, right, to neutralize our solution. To neutralize sodium hydroxide, right? So therefore his concentration will definitely be higher. All right, ladies and gents, that is the acids and bases as question. Honestly speaking, I think they were quite lenient here in that they didn't give us the back titration questions, right? And we'll move on to question 6. It says Sam wrote the following cell notation to represent a galvanic cell, right? So there's our galvanic cell notation there. They say complete the above cell notation to include the one important component that Sam left out. Okay, standard conditions were not required. Okay, so what is it that Sam would have left out? Sam left out the fact that when we use a gas which the chlorine chloride half cell is, we usually use platinum just to indicate there. Well, I didn't actually need to indicate the phase there. Or you can use carbon. Okay, so in this case, this is for electrical contact, right? All right, so in this case, they say define anode. Okay, remember, we define the anode as the electrode where oxidation takes place. So electrode where oxidation takes place. All right. Okay, the next one, they say identify the anode in the cell. Now remember, for the standard, for the galvanic cell, you always have the anode on your left-hand side, right? For in your cell notation, right? The one on the left-hand side would always be your anode, okay? If you don't understand what I'm talking about, please watch my full video on electrochemistry. Right, and then this is the Fe, okay, or you can say it is ion, right? Okay, now they say to you write down the net ionic equation for this reaction, for the reaction that takes place when the cell operates. Now, ladies and gents, what I'm just simply going to do here, when you copy them down, I don't have the standard cell, the half cell here, but I just copied it down for this question, right? So you've got Fe3 plus 3 electrons, right? And you note that we've got Fe3 plus, right? That's why I use that one. Remember that ion has got different ionic states, right? So which gives us Fe. But you also have Cl2 plus 2 electrons, which will give you 2Cl minus, right? And what you'll note there is that we said ion is our cathode, all right? Is our anode, rather. So we know that we're going to write this the other way around, right? And so this one we will keep the same, okay? Right, so I'm just going to show you in this case. So you end up with Fe giving us, this is the actual reaction that takes place. That's 3 electrons, okay? And now for chlorine, you've got that Cl2, okay, plus 2 electrons, give you, okay, note with one arrow, give me 2Cl minus. Now, ladies and gents, for us to write the net ionic equation, it is important for us to balance out the number of electrons, right? So that's the part I wanted to show you. So in this case, look at that. We've got 3 electrons here. We've got 2 there. So the lowest common multiple in this case between 3 and 2 is 6. So what I'm going to do is multiply that by 2. And I'm going to multiply all of that by 3, right? So what would I actually have at the end, right? My electrons would be 6, 6 each, so that would cancel out. So I end up with 2Fe, right, plus 3Cl2, which would give me 2Fe3 plus, now note this one was 2 already, so that would be 6Cl minus. Okay, so that is the net ionic reaction. What you can do is just multiply the 2 throughout and multiply the 3, and so that you can get that. Okay, right, I hope that makes sense. They say for this cell to operate, standard conditions of Fe3 plus and Cl minus need to be prepared, right? So they say define standard solution. What is a standard solution? It's a solution of known concentration. Okay, right. Please remember that. We've got a solution of known concentration. Okay, right. Now they say the standard solutions are prepared using ionic salts. Okay, that's iron nitrate and calcium chloride, right? They say what should be the concentrations of these solutions be? Okay, now what I want you to note in this case, remember, so for iron nitrate, that should be 1 mole per cubic decimeters, right? So that's 1 mole per cubic decimeters. Right, now note in this case that for calcium chloride, no? Okay, so what should happen in that case? It should actually be 0.5 moles per cubic decimeters. Okay, and in this case, of course, that's because of your net ionic reaction there. Okay, so so that we've got standard solutions. Okay, all right, now let's go to the next one. They say for this cell to operate at standard conditions, the atmospheric pressure must be 101. No, it's actually not the atmospheric pressure. It must be the pressure of the gas that is used, right? So they say correct SEM statement. Okay, so it's actually the 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 pressure. Okay, so it must be the pressure of the what was the gas that we used there? It was chlorine, of a chlorine gas. Okay, must be 101 or 1.01 times 10 to the power 5 pascals. Okay, right, so please keep that in mind. All right, and then they say to you, calculate the standard cell potential for the cell. Now remember, you already know what the which one is the anode and which one is the cathode, right? So we're going to just say E cell standard. Okay, that's going to be E cathode minus E anode. Okay, right, so you just read that off from your cell, and please make sure that you take the correct ion, right? It's 1.36 minus, remember in this case for chlorine, that's just simply that's chlorine, and this is iron, 0.04. Okay, and in this case we get 1.4 volts. Okay, so that's our answer right there. Now they say to us, SEM adds silver nitrate solution for to the chlorine half cell, causing solid silver chloride precipitate. How will this affect the voltage? Circle the correct option between the brackets and explain the answer. Now note, ladies and gents, so if I'm going to form precipitates, remember these are not soluble, right? So in this case, so what should happen in that particular cell? Okay, so our voltage in this case should actually increase. Now let's go back to the half cell, right? So what will happen? It means that the silver is going to take away the chloride ions, right? So it's decreasing the chloride ion. Now remember Le Chatelier's principle. The moment I decrease chloride ion, the reaction that favors the production of chloride ions will be favored. So the forward reaction occurs even more. Okay, and as a result, it means that my EMF should increase. Okay, so firstly, the voltage of the cell will increase. Okay, right? So what would be the reason? A decrease, there would be, okay, adding silver or Ag will decrease chloride ions, Cl minus ions, right? Okay, and in this case, it means that the forward reaction will be favored. Is favored. Okay, and it's favored to try and replace the Cl minus ions, right? And so what happens in that case? It means that my EMF will therefore increase. Okay, right. So remember, you always answer those questions by looking at Le Chatelier's principles. Right. Remember, if you change any of the solid or liquid as something that's in liquid, in that case, it will not affect, the reaction. But definitely, if it's aqueous solutions and gases, it will definitely affect the solution. All right, ladies and gents, I think we're ready to move on to question 7. All right, question 7. It says in both cells shown below, a concentrated aqueous solution of copper sulfate is electrolyzed using pure electrodes. All right. Now, if you look at cell A, you've got copper in both electrodes. So definitely that has to tell you that we are purifying in that case. And if you look at, cell B, right, you've got graphite rods, right, in the presence of that aqueous solution of copper sulfate. So in that case, definitely it means that we are looking at the process of electrolysis, right? Now they say to you, circle the correct answer. In cell A, rather, circle the correct answer, right? Now they say at the cathode. Now remember, at the cathode, this is where reduction takes place, right? Because we are talking about the process of purification. So we'll be reducing copper 2 plus ions to becoming copper, right? Because we're trying to purify copper. Right, so at the anode, okay, what will be oxidized there again? All right, so you're looking at copper being oxidized, right, to form copper 2 plus. Okay, and they say the concentrated solution as the time passes will. Remember that it will definitely remain constant, okay, because the rate of oxidation, same as the rate of reduction. So as a result, our concentration remains constant. All right, now we're going to cell B. Okay, so they say write down the chemical symbol of graphite. Remember, graphite is nothing else but carbon. Okay, our good friend carbon there. All right, and they say give a reason why graphite can function as an electrode by referring to the structure. So remember that graphite, or rather carbon, has free electrons, right? So it has free, or you can even say delocalized electrons, right? Localized. Okay, so that's why we would use graphite. Okay, so in this case, let's look at the next one. They say circle the correct answer between the bracket. Okay, at the cathode. So remember, at the cathode, this is where reduction is taking place. Okay, so what are we doing? In that case, what you will be doing is your cathode, this is where your copper 2 plus, all right, would actually be reduced. Okay, so copper 2 plus will definitely be reduced. Okay, for those of you who've seen me do this, said at the negative electrode, this is where we're going to have copper 2 plus ions being attracted there, and as a result get reduced. Right, what about the anode? Right, so what will happen at the anode is that now we will be oxidizing H2O in that case. All right, so we oxidize H2O, and what we actually form is the hydroxide ion in that case, right? They say the concentration of the solution as time passes will definitely decrease, right? Because you're using up that solution in order to form other products, right? Okay, so going right along to the next one, they say to us you are required to plate, okay, a lead rod with nickel. So remember, you would have had lead and you are now trying to coat it with nickel, right? Now, what I said to you, for those of you who've seen me do this, is that the one that you're trying to electroplate, you'll always put on the negative side so that it becomes, oxidized. Reduced rather. Okay, and then obviously the other one you'll put on the other side, right? So definitely I can note that nickel would be on the negative side, meaning lead would be on the positive side. Now, they give us an aqueous solution of lead nitrate and nickel nitrate, and they say give a formula for lead nitrate. Now remember that lead has got an oxidation number of 2 plus, right, and nitrates 1 minus. So you actually need 2 nitrates with 1 lead. Okay, so that's how we would write it there. They say choose from the bulleted list the above to label the diagram of the setup. Now remember, on the positives, on the negative side, I said this is where we put the one that we're trying to electroplate with. So we're trying to put lead, we will put lead there, right? That's the one that we are using to electroplate nickel. So nickel would be on this side here, okay? And now, when you put the salt solution, okay, the electrolyte, right, it will be the electrolyte of the one that you are trying to use so in this case it would be a nickel nitrate, right? So what we'd do is we would have a nickel nitrate over there, NiNO3. Okay, so yeah, we can write that out. I was actually lazy to write it out. Nitrate. Okay, so in that case, that is the one that you want there to perform the ion exchange through. Right, I hope that makes sense, ladies and gents. Right, so remember, we are required to electroplate, in this case, a lead rod with nickel. Okay, so we will do everything in our power. This is the one that we are electroplating with. Okay, so that is how the cookie crumbles. Okay, so let's go on to the next question. After 30 minutes, right, of the electroplating process, the mass of the lead rod has increased by 1.1 grams. Okay, they say calculate the number of electrons needed to produce the increase in mass. Okay, so now what are we going to do there? Right, so we're given the mass, the change in the mass of lead, right? Okay, they said the mass of the lead rod. Now remember, the mass of the lead rod would have increased because of nickel, right? Remember, what did we do? we electroplated lead with nickel. So nickel is the one that's causing that change in mass, right? So what I'm going to do is I'm going to say, well, the number of moles, right, of the nickel that would have formed, that's mass divided by molar mass. Okay, and in this case, I've got 1.1 grams, okay, divided by, if you check in your periodic table for nickel, we actually have 59. There it is. Okay, so it's 59. Okay, of course, you would have gotten this from your periodic table. And so what do we get? Okay, so we're going to say 1.1 divided by 59. I get 0.01. Okay, I'll say 186. Okay, so this is moles rather. So this is 0.0186 moles. Now, ladies and gents, I want you to please note, remember, for nickel, right, so it's Ni, okay, what happens to it? So nickel gets reduced in this case, okay, and forms around the lead, right? So for every 1 mole of nickel that forms, we would have used 2 moles of electrons. So which means, therefore, the number of moles of the electrons will be twice the number of moles of nickel. So this will be 2 times 0.0186. Okay, and in this case, I simply take that number multiplied by 2. Okay, and I get 0.037. Okay, 0.037. Well, I had 3 decimals there. Actually, yeah, maybe let's say 373. Okay, right. That is how we'll get that number. Now they say, hence, calculate the average current that was maintained during this period. Now remember that current is charge divided by change in time, right? So we've got the number of moles of electrons, so we need to get the amount of charge in that case, right? So how are we going to get the amount of charge? Well, we're going to use Avogadro's constant first, right, to get just how many electrons there were. So the number of moles is always equal to number of particles, which are electrons in this case, divided by Avogadro's number, right? So, which means to get the number of electrons, we will simply say number of moles multiplied by Avogadro's number. So I'll say 0.0373 multiplied by Avogadro's number, okay, which is 6.02 times 10 to the exponent 23. Okay, right, I'll say multiplied by 6.02 exponent 23. Okay, I get 200. Ooh, that's a huge number. Okay, I'm gonna convert it to scientific. I get 2.24, right, times 10 to the power 22. Yeah, times 10 to the power 22. Okay, and by the way, this is electrons, right? Okay, right, now that I've got the number of electrons, ladies and gents, remember I want the charge, so I'll multiply that. I'll say, well, to get the charge, this will be number of electrons. So remember, from electrostatics, number of electrons is charge divided by the unit charge of an electron, right? So which means this number n, right, that's charge divided by the unit charge of an electron. So that means if I want the charge, okay, so yeah, I'm trying to just write it out. If I want the charge, it's going to be number of electrons multiplied by the unit charge of an electron. So it's going to be that number there, 2.24 times 10 power 22 multiplied by 1.6 times 10 minus 19, which is the unit charge of an electron, right? Okay, so let's do that. And we still have that number of hours there. Let's multiply it by 1.6 exponent minus 19. Okay, and I get a number 3,592. Okay, or you can say 91. Okay, so that's 3,591.59 coulombs. Okay, so that's the charge. And of course, now I can calculate the current, isn't it? Okay, that's going to be charge divided by change in time. Okay, so it's that number 3591.59 coulombs divided by, in this case, the time. So what did they give us? Did they give us anything in terms of time? They said 30 minutes, right? Okay. If I remember correctly. No, I've gone too far now. Okay, calculate, maintain during this process. Yeah, they did say 30 minutes, right? Okay, so I'm going to say 30 multiplied by 60. Remember, it has to be in seconds, right? And what do we get there? Okay, so this is divided by, so I'm going to say 30 times 60. All right, so I get 1.995. That's about 2 amperes, right? So that is actually equal to 2 amperes of current. All right, I hope that you understood that. So they say explain why it would not be possible under standard conditions to plate the lead rod with aluminium metal, right, from an aqueous solution of aluminium. Okay, right. Ladies and gents, to answer these kind of questions, you really have to go to your standard potential table, right? Now, if I check there quickly, I'll see that, right, so you are trying to plate aluminium rod, okay, with aluminium metal rather, with an aqueous solution of Al3 plus, right? But remember, in that case, water is actually a stronger oxidizing agent, right? So H2O would be a stronger oxidizing agent. Okay, oxidizing agent than Al3 plus. Okay, right, you'll see on your table there, depending on which one you use, okay, it's either above or below, right? But if you're looking at oxidizing agents, the strength of oxidizing agent, definitely H2O is much stronger, and in this case it would tend to be reduced, right? More than Al3 plus. Okay, so that is the reason. And that covers question 7. All right, we move on to the next one. Right, and so we begin with question 8. So they say to us the saturated hydrocarbon C5H12 reacts with chlorine as shown below. All right, they say state the general reaction type for this above reaction. Now, first of all, two things that you should notice. One, there's UV light, so it tells you that this is not a spontaneous reaction. And secondly, the fact that we've got an alkane, right? So this is a saturated hydrocarbon. So of course, we do know that when they react with halogens, they would actually undergo a substitution reaction. Okay, so that would be a substitution reaction. All right, the next question. Right, they say explain the meaning of the term saturated hydrocarbon. Okay, right, so what do we mean when we say that it's saturated? It means that all adjacent carbon atoms, right, contain single bonds, right? Or in this case, you can say it is a it is a compound with carbon atoms with a maximum number of hydrogens around each carbon. Okay, right, please allow me not to write that one down. All right, so they say to us in one experiment 45 grams of C5H12 reacted. They want us to calculate the volume of chlorine gas at STP. Right, so first of all, remember, what did they give us? They gave us 45 grams of C5H12. So let's find out the number of moles. We know that's mass divided by the molar mass, right? So we'll say this is 45 grams divided by, now the molar mass of it's actually a pentane, right? So that's 5 carbons, so that would be 5 times 12, okay, plus in this case we've got 12 times hydrogens. Remember, the molar mass of hydrogen is 1. Okay, so what do we get there? So that would be 45 divided by, so that's 5 times 12, so that's 5 times 12 plus 12 times 1, which is 12, right? I get 0.625 moles. Now remember, what is this? This is the number of moles of C5H12. But what do we want? We want to find out about chlorine, right? So what we are now going to do, all right, so the volume of chlorine gas that is needed, right? So let's check in the reaction. For every one of this, we need 2 moles of chlorine gas. So therefore, the number of moles of chlorine gas needed would be 2 times the amount of moles of pentane. So that would be 2 times 0.625. Okay, and so which means we take that number okay, let's say answer times 2. Okay, I get 1.25 moles. Right, now remember, we wanted the volume of chlorine gas needed, okay, that is at STP. So we know we know number of moles is volume divided by molar volume, right? And remember, what is the molar volume at STP? That is 22.4, isn't it? So we want the volume. We know the molar volume. We've got number of moles. So volume, right, if we cross multiply, volume would be number of moles times molar volume. So that would be 1.25, okay, multiplied by 22.4 cubic decimeters per mole. And in that case, multiplied by 22.4, I get 28. I get 28 cubic decimeters Right, I was just trying to check if my calculation on the calculator is correct. Okay, so 28 cubic decimeters, that would be the volume of chlorine gas needed, right? Now they say to us the percentage yield of the reaction was 76%. Calculate the mass of C5H10 Cl2 that was obtained. Now note, ladies and gents, the first thing that we're going to do, right? I want you to please note that we are going to consider the number of moles of that we used, rather, of the C5H12, isn't it? Right, so that number of moles says, right, we got that number of moles, we said that's 0.625. But what we find out is for every one of this, we get one of that, okay? Right, so which means, therefore, that the number of moles of, I don't know what that would be, perhaps 1,2 dichloro, in this case, pentane, right? So what I would do is say, all right, so we've got the percentage in this case, right? I'll get to the actual percentage later on. So firstly, let me find out. So the number of moles of C5, okay, please, I want you to follow, C5H10Cl2, right, would be equal to the number of moles of C5H12, right? Because it's because of that 1-to-1 ratio. So that's 0.625 moles, right? And now, to find the mass, we're going to say number of moles is mass divided by molar mass, but we know if we cross multiply, mass is number of moles times molar mass, right? So the mass that we would obtain, now note that we would obtain if we had 100% yield, right? That's number of moles multiplied by molar mass. That would be 0.625 multiplied by, again, please help me out, I've got 5 carbons, so that's 5 times 12 plus 10 hydrogens plus 1 times 10, okay, plus chlorine is 35.5, right, on your periodic table, times 2, okay? So that's 35.5 times 2. Okay, so in this case, what do we do? Let's say 0.625 into 5 times 12 plus 10 plus 35.5 times 2. Okay, so I get a number 82.5. Okay, perhaps yours might be slightly different, I'm not sure, because I'm I'm not using the periodic table that was provided by the IEB, but please do check for me if you do obtain the same answer, right? Okay, so I got 82.5. No, man. No, I actually said 10, yeah. Let's say plus 10. Okay, 5 times 12, plus 10, plus 2 times 35.5. All right, yeah, there it is. Because I tried this earlier on. I get 88.125, okay, grams. I'm not going to round it off as yet. I'll round it off as the final answer. Right, now this would be the mass that we would obtain at 100% yield. But they said our yield was 76%. So the mass that we would obtain, right? So the mass at 76% would be 76 over 100. okay, multiplied by 88, 82, okay, 0.125. Okay, so essentially multiply that by 0.76. Okay, I get an answer of 66.98. Okay, so 66.98 grams. That would be the mass that I would obtain, ladies and gents. I hope that you got that. Okay. Right, so let's go on to the next question. They say one possible product of the reaction has the structure shown below. Give the IUPAC name of this compound. All right, so first of all, I want you to note this compound has got the longest chain is this guy over here, right? So that would be right, our chlorine is at carbon number 1 and carbon number 4, and we've got a methyl there, right? So this would be 1,2 dichloro. Okay. No, not 1,2 rather, 1,4. No, it's actually 1,3. Sorry. That's carbon number 1, 2, and 3, and 4. Sorry about that. So that's 1,4. Okay, dichloro. Please don't forget the hyphen. Dichloro. Okay. And we've got a methyl at carbon number 2. So that's 2 methyl. Okay, a side chain. And this would be butane. All right, so I hope you got that. And of course, if you didn't get that, please watch my videos on organic chemistry. Right, so next one. They say write a balanced equation for the complete combustion of C5H12. Right, so I want you guys to please note. So we've got C5H12 plus oxygen. Okay, let me leave some space, which would give us, now please, I want you to note, we always get carbon dioxide and H2O as a product, right? So all we need to do is to balance that reaction out. We've got 5 carbons. Let's make that 5. Okay, right. So we've got 12 hydrogens. So how would I make this 12? Multiply that by 6. Now, please, I want you to note the number of oxygens now would be 5 times 2, which would be 10, and 6 times 1, which is 6. So we've got 16 in total, right, on the right-hand side. So to make that 16, we have to multiply that by 8. So that's a balanced reaction for that. Okay, right. Now, the next question, they say structural isomers of C5H12 are possible, right? So in this case, they say define a structural isomer, right? So we know that structural isomers are organic compounds with the same molecular formula, but different structural formulae, right? Please don't forget the plural at the end there, right? So different structural formulae, right? So they say write down the condensed structural formula of the isomer of C5H12 with the most possible branches. Okay, so I think the one that would have branches, I think it would be 3, right? And let's see, I think we can put the one branch here, the other branch there. Okay, so this is what it would look like. Okay, now they said to you write it in condensed form, right? So what we need to do is write it in the condensed form. So I always prefer to do this, ladies and gents, unless you can write it down you know, and that would be C. It's this carbon over here. I've got CH3, which are my branches, but I've got 2 of them. Okay, and lastly, I've got CH3. That's what it would look like in condensed form. Of course, this is the final answer. But as I said to you, I always prefer to write it down first before I actually, write down the condensed structural formula. Right, the next one, they say define functional group. Okay, remember that a functional group, all right, it's an atom or a group of atoms, right, that form the properties, the chemical as well as molecular properties of a compound. Okay, right, it's an atom or a group of atoms that forms the center of the chemical activities in a molecule, right? So that's another way of saying that. Right, so they say draw the formula of the functional group of pent-1-ene. Okay, functional group of pent-1-ene, right? Remember, so when we talk about functional group, that would have to be the double bond, isn't it? Okay, so we are going to show there. All right, so this is the double bond. So that's what it would look like. Okay, right, so they say write down the condensed structural formula of a positional isomer of pent-1-ene. Right, so condensed formula. So if it would be at carbon number 1, I can either put it at carbon number 2 or at carbon number 3, I think. Would that work? Yeah, carbon number 2. Yeah, I think carbon number 2. Okay, so I'd say CH3, that's C, with the double bond, so that only have 1 hydrogen, double bond there. Okay, and CH3, I mean CH2, we need 5 of them, CH3. Right, so this is what a positional isomer would look like in condensed structural formula. Right, again, if you prefer to draw it first and then write down the formula. Right, now they say to us dimethyl propene, right, is a chain isomer of pent-1-ene. Okay, would it be possible for us to have dimethyl propene? Okay, so let's see. So propene, it would have a double bond. No, it's not possible, because the only way that you can have dimethyl would be at carbon number 2, and you see now you've got more than 4 bonds around the carbon atom. So in that case, the answer is simply false. Okay, right, so this guy is not behaving. Okay, so they said to us, is it true or false? It would definitely be false. Right, so they say methyl but-2-ene is a chain isomer of pent-1-ene. Which of these 2 compounds will have a higher boiling point? Right, so definitely, right, now this one has a side chain to it. Okay, so it is more spherical, so it would have a lower boiling point, right? So they wanted to know which one. Okay, so it would definitely be pent-1-ene. Okay, right. And essentially, ladies and gents, that's how we come to the end of question number 8. We'll look at question number 9 next. Right, looking into question 9, the very last one. They say ethanol is a very useful compound. It can be produced by several different reactions. They say name the functional group of ethanol, right? Ethanol alcohols have got the hydroxide, or you can say the hydroxyl ion, okay? That is the functional group. So one example of the reaction producing ethanol is given. Okay, they're taking glucose there, fermenting, and it forms, alcohol and carbon dioxide. They say the products of this reaction have a similar molar mass. Explain why ethanol is a liquid at room temperature while carbon dioxide is a gas. Now remember, ethanol has got, so ethanol would have strong hydrogen bonds, right? Well, you can also specify in addition to the London forces, right? So ethanol has strong hydrogen bonds. Okay, has strong hydrogen bonds. Please, I'll just shorten this. H bonds, you can say in addition to London forces. Okay, while carbon dioxide just simply has got weak London forces, right? Has weak London forces. All right. And therefore, more energy is required to separate the molecules of ethanol. So more energy is required. And of course, every time we explain this, we must actually emphasize this part. More energy is required to separate the molecules of alcohol, right? The molecules of alcohol than carbon dioxide. And so that is why it will actually become a liquid at room temperature. Okay, so the next portion, right? Ah, man, this guy. Two other reactions by which ethanol may be produced are shown below. Right, so here we are taking ethene and reacting it with reactant A to form ethanol. Please note we just form ethanol and nothing else. All right, so that tells us that we must have reacted this with water. That's a hydration reaction, right? So in the next one, we're taking B with potassium, a strong base, right? Potassium hydroxide, and it forms ethanol there. But note we've got potassium chloride. Okay, so it tells us that in that case, definitely that must have been one of those reactions where we take the dilute strong base. Okay, so B must have been, right? Now, first of all, there's our clue, ethane. We took the OH from the base there, right? But we must have had chlorine in there, right? So definitely that's going to be a chloroethane, isn't it? Now they say to us identify reactant A. Okay, so that would be water. So that's H2O, or you can write it in words and say water. And then give the IUPAC name of reactant B. I did say that must have been chloroethane. Okay, that's chloroethane. And then they say state the specific reaction for reaction 1. All right, so in that case, please, I want you to note that must have been a hydration reaction. They said specific, so that's definitely going to be hydration. And of course, reaction 2 must be hydrolysis, right? Okay, so that's going to be hydrolysis. Again, if you do not understand this portion, I think you might want to visit my my videos, okay, on organic chemistry. Right, now they say to us ethanol can be used to prepare the compound ethyl hexanoate. So in this case, remember, so that means we would have taken ethanol here, right, and the carboxylic acid would be hexanoic acid, right, to form that. All right, and they say which has a fruity smell. That's the characteristic of esters. They say name the homologous series to which ethyl hexanoate belongs. We've just specified that. That belongs under esters. Okay, they say give the IUPAC name of the compound X in the above reaction equation, right? Definitely that's going to be hexanoic acid. Okay, they say identify compound Y in the above equation. Okay, remember that's a condensation reaction, so that means that water is produced as well. And they say identify a suitable catalyst for this reaction. Remember, we always use concentrated sulfuric acid. Okay, and by the way, you can write all of these in words. For me, it's much easier to write them as in chemical formulae. Okay, as chemical formulae rather. Give the IUPAC name of a straight chain functional isomer of ethyl hexanoate. Now remember, guys, that functional isomers of esters rather, are carboxylic acids, right? So in this case, what would be that carboxylic acid? So remember, I've got 2 carbons here. I've got another 6 there, right? That would be 8 carbons in total. So that has to be octanoic acid. All right. And that is how the cookie crumbles, ladies and gents. We are done. Okay, and you would have earned yourself 200 marks. All right, so we come to the end of this paper, right? And I hope that you guys understood this very well. I shall see you guys again next time. From me for now, it's sharp sharp.